All right, lecture 2 of the exam 3 review. After talking about elementary reactions and mechanisms, we explored the behavior of 3 different simple mechanisms. The first one is the first order reversible mechanism, from which you can write a rate equation for A and also a rate equation for B, but it turns out that that's equivalent to the one for A, so there's really only one independent rate equation. And if you ask what happens given that rate equation, what happens at equilibrium, you can set that rate to 0 because of course the rates go to 0 at equilibrium. And then you discover that the equilibrium constant has to be equal to the ratio of the forward rate constant to the backward rate constant. And I said earlier that that's true even in much more complicated cases. For every pair of first order reactions like this, well, for every pair of elementary forward and backward elementary reactions at all, the equilibrium constant for that part of the mechanism is equal to the forward to the backward rate constants, the ratio of forward to backward rate constants. That's called detailed balance. And the important thing about it is that it gives us the connection between thermodynamics and kinetics. Kinetics contains the thermodynamics, as I've said before, and this shows at least one version of that connection, or that how that containment occurs. If you solve the differential equation using also the fact that A plus B has to equal the amount of stuff that was present at the beginning, then you get these expressions for how the concentrations change with time. And if you plot those expressions, we did it for several different special cases, but here's sort of a representative one, then you get a fairly simple decay of the initial product, initial reactant, down to an equilibrium value, and a fairly simple rise of the product B up to an equilibrium value. And you can show from the kinetics itself that the equilibrium values for both are equal to the rate constant for the backward reaction. Notice it's for A. It's the rate constant that creates A, right? The backward reaction creates A from B, so it's appropriate that it's the backward rate constant that appears here over the sum of the two. Or for B, it's the rate constant for the forward reaction, since that's what creates B, again by the sum of the two. And you can show, if you take the ratio of these two, that that's equal to K1 over K minus 1, which is equal to the equilibrium constant when you're at equilibrium. And so again, the connection to thermodynamics is clear. Also, these expressions that we derived strictly from kinetics could also have been derived, equivalent ones could also have been derived from thermodynamics alone without any reference at all to kinetics. So again, the two are consistent with each other. The second mechanism is the sequential mechanism. Perhaps this is the most important one of the 3 that we looked at. And that's a case where you have some reactant that then produces one product, and then that product goes on to produce a second product. In this case, B here would be, if the overall reaction is A goes to C, then B here would be an intermediate. So part of the reason that this mechanism is important is because it's got an intermediate in it, and we can see what happens with that intermediate. If you solve the rate equations, I won't even write the rate equations down in this case, but if you solve them, you get these expressions. Notice that the first one here is the same as the first order integrated rate law that we looked at earlier. In other words, A disappears or is destroyed in exactly the same way as if these other things weren't present at all. In other words, all this stuff doesn't have any effect on what A does, and that's because the reaction is irreversible. Once you've gone to B, you can't have any more effect on A, right? B can't go back, and so neither can C. And so it's not surprising when you look at things that A behaves as if it were all by itself. These other two are described in the case of the intermediate I. Actually, in keeping with how this was, what I call these things in the original notes, let me call them I and P, and down here too, whoops, for I, this function, I mean, it's not obvious if you look at it carefully, you can see how it works, but describes a buildup and then a decay as I is first created from A and then is destroyed again in order to create P. And then P describes a delayed buildup because, oops, gosh, I've mislabeled everything here. That's P. And this is I. Because everything has to end up at P at the end. These are both irreversible reactions. Where are they? Here they are. Got so much pink junk on there, I can't see them anymore. Since both of these are irreversible, everything has to end up at P in the end, right? However long it takes, you can't go backwards. So once you start destroying A, it's gone forever. Once you start destroying I, it's gone forever. Everything has to build up on P. P is a trap, if you like, in this mechanism. Any kind of irreversible step always creates traps in chemical mechanism. So everything has to end up on P, but it takes a while for P to begin building up because before you can get any P, you have to create some I. So it's a delayed buildup. For the third mechanism, which is the branched case, there are a couple of consequences that come from this, right? This intermediate is especially interesting, but we'll talk about relative to the steady state approximation and the rate limiting step ideas, but we'll talk about those below. Let's talk about the third mechanism, the branched mechanism first. This is a case where you start with one reactant and it goes to two different products with different rate constants, K1 and K2. In that case, here's the solved expressions again. And again, the rate at which A goes away is as if there were no C or B because these are irreversible steps again. But notice that A goes away now with a decay constant or effective rate constant that's equal to the sum of both of these two rate constants. And that's because A has two channels by which it can go away, right? It can go away this way, it can go away that way, and those two ways are independent of each other. A goes away this way at the same time that it's going away that way. And so it's like, you know, having a pool of water with two garden hoses leaking out. You get the total amount of water, the A in this case, draining out of the pool at a rate that's the sum of both garden hoses. Both of these channels, or reactions if you like, are functioning the way a garden hose would in that case. And so it decays more quickly than it would if only one reaction were active. And then the other two, nothing, once B is created, it can't go back. And so things just build up on B, things just build up on C. And so these are two simple first order buildup curves. Here they are down here plotted. And the only difference is that they arrive at ultimately at different amounts of stuff depending on which of the two branches has the faster rate constant. The faster branch wins, quote unquote, which means that there's more of it at the end, right? Everything has to end up as either B or C, because these are both traps in this case. Can't have any A at the end. But you can have more B or more C depending on which of the two rate constants is actually faster. The ratio of the final total amount of C to B is the same thing as the ratio of the two rate constants. And the total amount of B at infinity, at time infinity, and C are given by these relationships. They look a lot like the relationships for the equilibrium concentrations of A and B for the reversible reaction, but though they are similar mathematically, they're describing completely different behavior in the mechanism itself. And again, you can see that if K1 is bigger then B, we're going to have more B. If K2 is bigger, then we're going to have more C at the end. All right, that brings us to these two approximations or ways of understanding mechanisms. One is the steady state approximation. It happens that if you're trying to write an overall rate equation for a mechanism, let's say for an overall reaction, A goes to C, maybe there's a bunch of intermediates in there, B, D, E, G, H, a whole bunch of other molecules that act as intermediates. Very likely, if you write the rate of change for C from the mechanism, it's going to involve all these intermediates, and that's no good for practical purposes. You want to eliminate them. You also want to understand the mechanism better, and for both of those purposes, the steady state approximation is useful. The way you go about doing it is you write rate equations for all of the intermediates, all these guys, and then set them all to 0, and having set them all to 0, you solve for the intermediate concentrations in terms of the non-intermediate concentrations, or the majority species concentrations, and then use those to replace the intermediates in the final rate law. So let's look at an example. The overall reaction is A goes to C. Our mechanism is our simple sequential mechanism. A goes to B goes to C as above, with K1 and K2 here. And B is the intermediate, as I pointed out earlier. The rate of change for C, that is the rate of reaction of the production of product, would then be, by this mechanism, would just be K2 times B. But B is an intermediate, so this is a bad rate law, not a very useful rate law. To eliminate it, we use the steady state approximation. So we set the rate equation for the intermediate B to equal to 0. That allows us, notice you could solve for B directly, but notice that the quantity we actually need to replace, K2B, is going to be already equal to K1A, so we can just replace that K2B with a K1A, and that says that the rate is equal to K1A. A is a majority species, it's one of the reactants, and so that's a good rate law. The idea of a rate-limiting step, I think probably everybody is familiar with already. It's commonly taught in freshman chemistry and probably in other classes too. The idea is just that if you've got a chain of reactions like this, so a sequential reaction with lots of steps in it, or any number of steps in it, but one of the steps is much slower than all the others, let's say at least 10 times slower than all the others, then that one step dominates the overall rate, and the overall rate will be about equal to what it would be just from that one step alone. Finally, that's sort of the overall of the mechanics or kinematics, if you like, of chemical kinetics. The next major topic, the third major topic, is understanding this somewhat mysterious rate constant. And let me say that I've said this before, but we're just scratching the surface here. The rate constant is a complicated thing. A lot of all the molecular detail, all the quantum mechanics, all the complicated, nasty, complicated stuff is buried in that rate constant. So we're just scratching the surface on rate constant theory here. We're going to talk about Arrhenius theory and Eyring theory. They're almost the same thing. Eyring just gives us a little bit more insight into what's the nature of this transition state. So the most important idea really from this section is the idea of a reaction energy diagram, which shows how the energy of the system changes as you move along a reaction coordinate from the reactants to the products. The idea of a transition state is that as you go from reactants to products, you have to first go up in energy before you can go back down in energy to reactants. At the top of the energy hill is the transition state, which, as we've seen, is something sort of intermediate on the way between reactants and products. That makes sense. And is unstable, right? If I tweak it in one way, I'm going to go back to reactants. If I tweak it in the other way, I'm going to go back to products. So it's not a stable species. It's not something you can put in a jar. It's something that exists only for a fleeting moment of time and then transitions off, hence the name transition state, to something else, to reactants or products. The top of that barrier, the height of that barrier is important for the rate of reaction according to Arrhenius theory and Eyring theory, both, and according to sort of intuitive logic too. And that height is the difference in energy between the reactants and the transition state. There's a height, there's an activation energy for both the forward direction and also for going backwards, right? We can start at products and go backwards, or we can start at reactants and go forwards, and so there's a backwards activation energy as well. And the difference between those two is the thermodynamic delta H, or something very close anyway. It depends exactly what you mean by this diagram, but can be exactly the same thing as the thermodynamic delta H enthalpy change for the reaction. We'll take that to be the case in this class. I'm skipping, many subtle difficulties and stuff, so please, if you end up in a research area in your future career that involves a lot of kinetics, don't fault me too hard for skipping over some of the details here. All right, Arrhenius theory says that the rate constant for an elementary reaction is equal to a pre-exponential factor A times an exponential factor e to the minus EA over RT. We saw that you can interpret this factor as the rate at which the reactants make the attempt to get over the barrier, but they're very unlikely on any one try to get over the barrier, because there's also another factor that gives the probability of success in getting over that barrier. And that depends on the height of the barrier, and therefore depends exponentially on how high that barrier is. Very sensitive to the height of the barrier. And it tends to be a very small number, which means that this has to be a very large number in order to get an appreciable value for K. Eyring theory is very similar. This exponential factor is almost the same thing as e to the minus EA over RT, because EA is almost the same thing as delta H double dagger. This is the enthalpy of the transition state itself. Delta H double dagger, anything with a double dagger on it, refers to a property of the molecule in the transition state when it's at the top of the barrier. But this pre-exponential factor has been replaced by something that's quite a bit more complicated and involves these quantum mechanically derived factors in front and an exponential that involves the entropy at the top of the barrier, the transition state entropy as well. So entropy considerations enter into the effective attempt rate within Eyring theory. And also because these are delta H and delta S for something that has physical meaning that we saw. I won't go through it in this review, but we spent some time talking about what transition states are like. You can get a physical picture for what those things are like, and therefore you can get a physical picture for what these delta H and delta S values ought to be, at least rough, and sometimes they can be quite accurate. All right, that gives a set of relationships. The energy of activation is about equal to the enthalpy of the transition state, and the pre-exponential factor is more or less related to all these quantities. That means you can invert right in order to find the delta S of activation, and it's related to the pre-exponential factor in this way. All right, then we also talked about how the rate constant depends on temperature. That's one of the main things that Arrhenius theory and Eyring theory gives us, after all. One of the main kinds of problems that you encounter is you're given some data on how the rate constant depends on temperature, and you want to use that to extract the activation energy and ultimately the pre-exponential factor. This two-point form, which we derived earlier, is useful for that. It's the same thing as the Van Hoff form if you replace this with delta H instead of energy of activation and replace these guys with equilibrium constants instead of rate constants. So mathematically it's the same thing and therefore should be familiar. Especially you can make a linear plot by plotting the the logarithm of the rate constant as a function of temperature versus 1 over the temperature. That should be a straight line according to Arrhenius, and the slope should be minus EA over R. The energy of activation is always positive, which means that in an Arrhenius plot like this, you'll always get the slope going downwards, never up. And it also means that the equilibrium constant, or sorry, the rate constant always increases with time, with temperature. Chemical reactions always go faster when you raise the temperature. There are a whole bunch of relationships because of this diagram, because of the fact that these three quantities are related to each other. There's a whole bunch of relationships between the forward properties, forward activation energy, forward delta H, forward delta G, forward delta S, and so on, the reverse properties, and the equilibrium or thermodynamic properties, and here they all are. There's also, of course, this one, which relates a thermodynamic property to a forward and reverse property. And I won't go through them all, just remember them all, put them on your notes or something like that, and you can find all these relationships with relative ease. And that is it for our review. Good luck to everybody on the exam, and if you have questions, well, there'll be one more recitation section on Monday right before the exam, but you can also come to my office hours on Friday at 4, and if you really want some answers from me, send me an email.